In 2024, Super Typhoon Uwan was expected to be just another storm, until within a single night its winds exploded past 300 kilometers per hour, overwhelming every forecast model and leaving millions scrambling to survive. Official reports blame data gaps and model confusion, but the real cause was deeper and more elusive. Could our best technology predict the next Uwan before it is too late? Or are we still blind to the unseen forces brewing beneath the Pacific? The answer reveals what is truly at stake and what remains dangerously unknown. 48 hours before Uwan's landfall, the world's top forecast models split by more than 600 kilometers. The Joint Typhoon Warning Center issued track projections that veered north toward Taiwan, while the Japanese Meteorological Agency's path curved sharply west, threatening Luzon. In real time, meteorologists watched as satellite images flickered with dense cloud cover, key details obscured by interference at the storm's core. Analysts at the Joint Typhoon Warning Center flagged the missing data, noting that cloud top interference had blocked critical readings just as Uwan began to accelerate. Behind closed doors, Japanese Meteorological Agency specialists pored over model outputs and live feeds, searching for any sign of the storm's true intentions. It wasn't until the post-storm forensic review that the blind spot became clear. A warm core ocean eddy, hidden beneath the surface east of Luzon, had gone undetected by every operational model. This deep pool of heat, unmeasured in real time, fed Uwan's rapid growth, fueling a surge that models failed to catch. The mist anomaly exposed a fundamental weakness. Even with a torrent of satellite data, gaps in subsurface ocean monitoring left forecasters guessing. For the men and women tasked with predicting the next move, these unseen forces meant the difference between a warning delivered and a warning delayed. Rapid intensification remains the toughest puzzle in typhoon forecasting. Scientists define it as a jump of at least 56 kilometers per hour in sustained wind speed within a single day, enough to turn a moderate storm into a disaster overnight. For a storm to reach this explosive threshold, ocean waters must be warmer than 28 degrees Celsius, with deep layers of heat stretching far below the surface. During Uwan, the Philippine Sea registered some of the highest ocean heat content on record, creating an environment primed for sudden escalation. Even a 1-degree increase in sea surface temperature can raise a storm's potential intensity by about 3 to 5%, according to NOAA research. That means as the oceans warm, the odds tilt further toward rapid, unpredictable surges in strength. Yet, models still miss these leaps more than 40% of the time. The problem is not just the atmosphere. It is the hidden layers of the ocean and the fine-scale bursts of energy that standard forecasts cannot resolve. Dr. Elena Cruz, a lead modeler, describes the challenge as trying to catch lightning in a bottle. Her team is now working with the Hurricane Analysis and Forecast System, HAFS, which couples high-resolution ocean and atmospheric data. Early results suggest HAFS could improve rapid intensification prediction by 30 to 40%. But even with cutting-edge tools, the chaotic nature of these storms keeps forecasters on edge, knowing that the next Uwan could still outpace the best algorithms. Every 30 seconds, a fresh image of the Western Pacific flashes across the screens at weather centers from Manila to Tokyo. This is the new normal, powered by GOES-18 and Himawari-9 satellites. Their sensors pierce through dense cloud layers, capturing the heartbeat of a storm in real time. Sea surface temperatures, swirling moisture, and the hidden structure of clouds, all mapped in stunning detail. For the first time, forecasters can watch the inner core of a typhoon shift and stretch as it feeds on warm ocean water. Synthetic aperture radar, SAR, adds another layer, mapping wind fields inside the storm's eye with a clarity that was impossible during Uwan. These radar snapshots reveal twisting bands and sudden bursts of energy, the subtle signs that can warn of an impending surge in strength. The data stream is relentless, more than 20 terabytes of meteorological information every day. That is enough to fill thousands of laptops, all devoted to tracking the smallest changes in the atmosphere and ocean. With this torrent of data, the old blind spots are shrinking. Where once a typhoon's most dangerous moments played out unseen, now every flicker of intensification is recorded and relayed to supercomputers and forecasters alike. The ability to see inside the storm, moment by moment, has transformed the science of typhoon prediction. For the people in harm's way, it means warnings can arrive with greater precision, sometimes hours before disaster strikes. Artificial intelligence now sits at the heart of typhoon forecasting, turning the flood of raw satellite and ocean data into earlier, sharper warnings. In late 2023, Google DeepMind's GraphCast model stunned the meteorological world by accurately predicting global weather patterns up to 10 days in advance, outperforming legacy models in 9 out of 10 test cases. IBM's Graph system, operational since 2022, pushes updates every hour instead of the old 6-hour cycle, offering a near real-time window into a storm's evolution. These AI systems sift through radar, satellite, and buoy feeds, searching for the subtle anomalies, tiny spikes in ocean heat or sudden shifts in atmospheric moisture that so often precede explosive intensification. Sharper warnings. The gains are real. During recent storm seasons, AI models have flagged pre-storm heat anomalies invisible to human forecasters, sometimes narrowing the warning gap by hours. But the technology is not flawless. Even the most advanced neural networks struggle with the chaos of microscale convection, those swirling, unpredictable bursts inside a storm that can tip the balance from steady growth to runaway intensification. Dr. Raphael Lim, a senior AI researcher at Pagasa, puts it plainly. AI can spot patterns we miss, but it still can't see every spark that lights a superstorm. Limits remain. The promise of AI is speed scale, analyzing terabytes of data, catching the earliest warning signs, and delivering updates fast enough to matter. Yet for all its power, the technology remains bound by the limits of data quality and the unpredictability of nature. The next breakthrough may arrive in code, but the search for certainty continues. Search continues. Across the globe, a vast network of sensors feeds the world's forecast systems. More than 10,000 ocean buoys, 400 weather balloons, and over 200 Earth-observing satellites scan the atmosphere and sea every hour. These instruments capture wind, temperature, pressure, and ocean heat, generating a torrent of raw data. At the European Centre for Medium-Range Weather Forecasts in Reading, England, supercomputers process over 500 million atmospheric observations every 6 hours. The sheer scale is staggering. Satellite radiances alone make up nearly all of it, with in situ readings from ships and aircraft filling the gaps. But the flow is not instant. Each new observation, from the Pacific to the Atlantic, faces a 15 to 30-minute delay before it reaches live forecast models. That lag, caused by downlink, processing, and quality control, can mean the difference between catching a storm's sudden jump in strength and missing it entirely. Even with the most advanced technology, the world's warning systems are still bottlenecked by the speed of their own data pipelines. Inside the Pagasa Command Center, the air thickened with tension as Uwan's wind readings spiked and model outputs clashed. Monitors glowed with conflicting tracks, while group chats and emergency lines buzzed with urgent questions from governors and local officials. One forecaster, still haunted by the memory, described the moment. He said they kept refreshing every source, waiting for agreement, and that every hour they waited, the risk grew. With no model consensus, evacuation orders for several provinces stalled, some delayed by as much as 12 hours. In those lost hours, families packed bags, checked phones, and waited for a signal that did not come. A University of Reading study found that when agencies clearly label uncertainty in their warnings, public trust rises by 45%. The lesson is simple. When officials know what is not certain, they act sooner. In the chaos of Uwan, the difference between a vague alert and a confident, transparent warning was measured in lives and minutes. The pressure to decide, without perfect information, remains the hardest storm to weather. Today, the Western Pacific faces a future where Category 5 storms are projected to become 20% more frequent by 2050. Technology races to keep up, but uncertainty remains. The next storm will come, and the true test is whether our choices outpace nature's fury or simply react to it.